Like, actually good or only good for smart people like you?
First, I'm not smart people, and second, he's actually very, you know, very nice guy, and actually a good professor, I would say. And he's willing to
Okay,
explain to everybody like 3 times.
so
Anyway, I'm gonna
today we're going over independence and a brief discussion of bivariate transformations. We'll discuss transformations in more detail next week. But there's a couple definitions of independence that are all equivalent to one another. The way I'm defining it for the purposes of these notes is probably the most intuitive way that we've basically seen before, that we say two random variables are independent if the probability that x is an element of some subset and y is an element of some other set is just the product of the individual probabilities. That's pretty close to the way we defined it earlier. Cassell and Berger defines it slightly differently, but there's a theorem in Cassell and Berger that says this definition is equivalent to their definition. So in English, that would be that all events defined in terms of x are independent of all possible events defined in terms of y. Note this has to hold for all possible events. If it's true for some events but not others, then the random variables are not independent. And you can show fairly easily that if x and y are independent, then that's equivalent to saying that the joint CDF is just the product of the marginal CDFs, with the possible exception of a few sets of measure 0. The actual precise mathematical term for that is f of x and y equals f of x times f of y almost everywhere, or almost surely. If you hear that term, it means everywhere except possibly on a set with measure 0 or probabilities 0. And similarly, there's a theorem that I'll discuss in more detail here in a minute that random variables x and y are independent if and only if the joint CDF is the product of the marginal CDF, or not CDF, the joint PDF is the product of the marginal PDFs, or likewise for PMFs for discrete random variables. So, how do you see if two random variables are independent? Well, first of all, their joint PDF or joint PMF has to have positive probability on a rectangular support. If that's not the case, then you already know that they're not independent. And a case where that wouldn't happen would be something like, oh, say for example, that you know that x and y are normal, and you're given that like x plus y less than or equal to 3 or something like that. This is just the first example that comes off the top of my head. If you plot x plus y less than or equal to 3, that is not a rectangle in R2. It'll be like half of the plane with a diagonal line separating the two. That's not a rectangle. Those two random variables can never be independent. And if the domain's rectangular, be another couple examples of joint random variables whose domain is not rectangular here in a few minutes. If the domain is rectangular, then you can try to write the joint PDF or joint PMFs, the product of functions of x only and y only. In fact, as I said, there's a theorem in Cassell and Berger that says that if x and y is a bivariate random vector, then they're independent if and only if there exists functions g that depends only on x and h that depends only on y, such that the joint PDF can be written as the product of the marginal PDFs. And as I said, if I remember correctly, the theorem on the previous slide, Cassell and Berger defines to be the definition of independence, but since it's an if and only if, that definition is equivalent to the definition that I gave earlier. As I was saying, an example of two random variables whose, well, I shouldn't confuse myself already, but so say we select 2 points randomly on a line of length A so that the opposite sides are on the midpoint of the line. And we want to find the probability that the distance between them is less than A over 3. So we define random variables x and y as follows. X is uniform in 0 to A over 2, and y is a coordinate between A over 2 and A, because we set this up so that the first one is in the first half of the line, the second one is in the second half of the line. And we're going to assume that they're independent of one another and they're uniform over the interval. They're equally likely to be any points in those intervals. So how would we find the probability that they're within A over 3 of one another? Well, since they're independent, the PDF of one of the individual variables, if you remember from a couple lectures ago, if a random variable that's uniform on the interval 0 to A has PDF of 1 over A. So a random variable that's uniform on 0 to A over 2 will have PDF of 1 over A over 2, or in other words, just 2 over A. So their joint density will just be the product of the two marginals, in other words, 4 over A squared. And so the solution, the probability that they're within A over 3 of one another is equivalent to the probability that the difference between the y point, which by definition is between A over 2 and A, so it's always going to be bigger than x. We want the difference between y and x to be less than A over 3. This is kind of what I was talking about before. We have to integrate over this region x minus y over 3. Now in this case, x and y are still independent because the support of this joint distribution is still rectangular in R2, but we're just integrating over a subset of that region. Now, if the support of this random variable were only this region, then they would not be independent, just as a quick aside. So the limits of integration here, they weren't in my original lecture notes, and I had to think about this for a minute. But in principle, x can go from 0 to A over 2. However, if we want the region where x and y are within A over 3 of one another, and if x is less than A over 6, the lower limit down there, really get better batteries so that I can actually see my laser pointer, that A over 6 is the lower limit of that first integral, because if x is less than A over 6, there's no possible value of y such that y minus x is less than A over 6. So the lower limit is A over 6. The upper limit is, of course, A over 2, because we've defined x to be uniform on 0 to A over 2. Now the limits for y, the lower limit for y is, of course, A over 2, because we've defined that y can't be less than A over 2. The upper limit, we want the region where y minus x is less than A over 3. So the largest that y can be and still be in this region is x plus A over 3. Hopefully you've all done multivariable calculus and remembered doing this in at least some previous life or something like that. I had to think about how to set this up for an embarrassing long time, because I honestly haven't done a multiple integral like this in years. But finally figured out the correct limits of integration and integrated it and came up with 2/9 that interestingly doesn't depend on A. I was sufficiently squeamish about this that I actually went into R and simulated a bunch of examples of this and got a probability of almost exactly 2/9 every time. So I'm pretty sure that I do in fact remember how to integrate and that this is right. So another example, kind of a famous probability problem that you may have seen before if you've taken probability in the class, is what's known as Buffon's needle problem. So the setup here is the table's ruled with lines distance t apart, and maybe I should have put a picture of this in the slide so it's easier to visualize. If you go to the Wikipedia page on Buffon's needle problem, they have like an animated GIF of this entire problem and how to solve it. It actually does a really good job of explaining it. Unfortunately, I don't think there's a good way to embed an animated GIF in LaTeX. So you'll have to content yourself with my ugly scribblings on the board. But the idea is, so we have this table with lines like this. The lines are separated by distance t. Well, let me give the full setup as I continue to draw the picture. So we're going to define two random variables x, or two random variables that we call x and theta, where x is the distance from the needle to the nearest line, and theta is the acute angle between the needle and the line. So let's say that needle lands right there. The needle has length L in our setup. That would be the center of the needle. That distance there would be x. This angle here would be theta, is the way we're setting this up. And those of you who are watching this on YouTube, I apologize for the fact that you can't see my ugly scribbles on the board. I suggest you go to the Wikipedia page and look at their animated GIF because it'll be a lot easier to understand than my scribbles anyway. So we're going to assume that x and theta are independent. You just throw this needle on the board, and the distance between between the center of the needle and the line is just uniform between 0 and t over 2. We're defining x to be the distance between the needle and the closest line. So if the center of the needle lands exactly on the line, x would be 0. Or if it lands exactly in the middle, x would be t over 2. It can't be any larger than t over 2 because it's always going to the closest one. And theta is going to be somewhere between 0 and pi over 2. That, in other words, between 0 and 90 degrees. No, I take that back. No, I guess that's right. That we're defining it to be the acute angle, so that if it's pointing in the other direction, you just rotate it. That makes the math slightly simpler. And since they're both uniform, both independent of one another, using the same logic that we had before, that means the joint PDF is 4 over t times pi. And the only thing that we have to do is figure out what region we need to integrate over. And this is when you have to try to remember some of your trigonometry, that the distance, the length of this segment here from the center of the needle to the end of the needle, that we can call big L, for instance, if you remember your trig, that, no, that isn't quite right. That distance is L over 2. So if you remember your trigonometry, that the total height, that the height of this piece here sine is defined to be opposite divided by hypotenuse. We know the hypotenuse is L over 2 here, so this height here is going to be L over 2 times sine of theta. And the needle will intersect the line if and only if this height here, which is the amount that the needle sticks up from the center, is bigger than x. In this case, it doesn't intersect the line because this distance here is smaller than x, but if the needle landed there like that, this distance here would be bigger than x, so it would intersect the line. So the region that we need to integrate over is the region where x is less than L times the sine of the L over 2 times sine of theta. So that integral is just integral from 0 to pi over 2, and the integral from 0 to L sine theta over 2 from of 4 over t times pi dx d theta, which turns out to be 2L over t times pi. That makes sense, more or less. Like I say, the Wikipedia page on this is really excellent, and if my explanation completely confused you, theirs is probably better. So, now going on to expected values of independent random variables. Recall that given any two possible events that, I don't think that's the way I've written. I think those should technically be Borel sets and not just any subsets of R, but whatever. The point is that if the probability that x is an element of some subset and y is the element of some subset is just equal to the probability that x is in that subset times the probability that y is in that subset, which is equivalent to saying the events corresponding to those, the set of omegas in the original outcome space such that x of omega is in A and the corresponding event for y are independent of one another. They said Cassell and Berger use a slightly different definition of independence, so they proved this is a theorem. We just took this to be our definition of independence. So, among other things, that if g is a function of x only and h is a function of y only, then the above implies that the expected value of g of x times h of y is just the product of the individual expected values. That, for instance, if x and y are independent of one another, the expected value of x squared times y cubed is just the expected value of x squared times the expected value of y cubed. You can find the expected values for x and y independently and then just multiply them together. But that only works if they're independent. That, for example, if you want to find the expected value of y to the fifth, you can't just find the expected value of y squared, the expected value of y cubed, and multiply them together, because in general y squared and y cubed will not be independent of one another.
That's just a fifth moment of y, right?
Right. And quick proof of this, showing the way it works in terms of integration. But the expected value of g of x times h of y is, by definition, this double integral of g of x times h of y times their joint PDF. Well, since they're independent, the joint PDF is just the product of the marginal PDF, so we can write it like that. And, of course, then everything that doesn't depend on y can come out of the x integral, and everything that doesn't depend on x can come out of the y integral. So you end up with just g of x times the marginal of x dx times the integral of h of y times the margin of y dy, And of course, that's just the definition of the expected value of g of x times the expected value of h of y. So, any questions about independence thus far? Okay, so now introduction to bivariate transformations. As I said, we'll get this in more detail for better or for worse next week. But let's say that x and y is some bivariate random variable with a known distribution, and we let u be some function of x and y and v be some other function of x and y. And these functions are defined to be probability mappings if given any Borel set in R2 that the probability that uv, the transformed variables, are contained in some Borel set B is just the probability that the original x and y are contained in some A, where A is the inverse mapping of B, that is, that A is the set of x's and y's, such that G1 of xy and G2 of xy are contained in this new set B, which theorem's a little funky, but if you think it through, it should agree with your intuition. This can probably be ignored at the MS level, but if you're taking 760, then you'll want to make sure you understand the more formal definition. And this inverse is well defined even if the mapping's not bijective. It's the same idea that we've done with these transformations of variables in the past, that if we define like y equals x squared, we can define probabilities on y even if x takes negative values. So this is just an example of two possible functions that, unless you're deliberately trying to break this by choosing some ridiculously convoluted functions, probably every function that you would ever care about in real life is going to satisfy the properties that I just listed here. And this becomes slightly simpler for discrete random variables, that if x and y is a discrete and so the probability mass function is positive only on a countable set that we call A, then u comma v, the transformed random variables, is also discrete and takes values on a countable set B. And the way you find this countable set B is you define this new set AUV to be the x and y in A such that G1 of xy is U and G2 of xy is V. Then to get the joint PMF for U and V, you just sum over the x's and y's such that g of x1, y1 gives you the u, and g2 of xy equals the v. I know that definition's a little non-intuitive and hard to grapple your brain around, but if you think through the math, it makes sense, and hopefully it'll make more sense when I do the example, a concrete example of this on the next slide. That, say for instance, we want to find the distribution of the sum of two independent Poissons, and yeah, I know you're probably saying this would have been useful to know before the midterm, Eric. Well, I wanted to help give you practice trying to think on your feet, but if x and y are both Poissons with parameters lambda 1 and lambda 2, and you define u to be the one that you really care about, the sum of the two, and v is just kind of a throwaway that you can use to grease these calculations a bit. So both x and y take on values in the support 0, 1, 2 up to infinity. So uv takes on the values, where v can take on whatever values it wants. U can only take on the values going from v up to infinity, because if y is equal to v, then x can't be any smaller, or then u can't be any smaller than v, because it's defined to be x plus y, so it goes from v up to infinity. So for some particular uv, the set of x's, the set of x comma y's that map to u comma v, all you have to do is invert this mapping and say that given u comma v, there's one and only one x and y that will map to this u comma v. It will be u minus v comma u. So then we use the formula on the previous slide to get the joint PMF of u and v. All we have to do is substitute u minus v comma u into the joint PDF of x and y. And since x and y are independent, that's just the product of the marginals. So we take the marginal for u, or the marginal for x, the marginal for y, and then plug in u minus v for x and v for y. So the right-hand piece there, you can see, is just the PMF for Poissons with rate parameter lambda 2 evaluated at v. The first piece is exactly the same sort of thing, only rather than an x, we substitute in u minus v for x everywhere we see it.
Is that second u, particular uv, the u minus v comma u, is that supposed to be a v?
Yeah. Yeah, maybe I shouldn't have used u and v because they may be hard to tell apart if you're sitting on the back row, but it's a v. So the distribution of u equals x plus y is just the marginal distribution for u. That is, you'll recall, we can extract the marginal distribution from the joint distribution by just summing over all possible values of the second variable. So we take this joint PMF, sum over all possible values of v. V in this case can only assume the values from 0 up to u, because any bigger than that in the sum would be greater than u. And if you pull the u factorial term and the minus lambda 1 plus lambda 2 terms out of the summation sign, and you have the sum from v equals 0 to u of u choose v times lambda 1 to the u minus v times lambda 2 to the v, which hopefully you recognize as just lambda 1 plus lambda 2 to the power u according to the binomial theorem. So that tells us that the marginal distribution of u, i.e. the distribution of x plus y, is just e to the minus lambda 1 plus lambda 2 times lambda 1 plus lambda 2 to the power u over u factorial. So, in other words, we've just proven that if x1 and x2 are Poissons, then with rate parameters lambda 1 and lambda 2, then the distribution of x1 plus x2 is another Poisson with rate parameter equal to the sum of the rate parameters of x1 and x2. And these sorts of things are worth remembering and possibly worth putting on your formula sheets for exams / qualifying exams and so forth, because this ends up, I don't know, I won't say this sort of thing never comes up in real life. I mean, I keep talking about my paper where I use the beta distribution, and it involves knowing that you can take like the sum of a bunch of chi-square random variables and do appropriate divisions and end up with beta. So it is sometimes useful in practical situations to know like the distributions of sums or products of random variables and so forth. But where it really becomes useful is when you're trying to think of an interesting quals question, and so having somewhere either on your formula sheet or in your brain what happens when you sum a bunch of Poissons or exponentials or gammas or whatever the case may be, worthwhile to know. And I think we'll give some more examples of this in upcoming lectures. And yeah, that's all I've got for this stuff. Any questions?
So the reason you're summing to U in this case has to do with because of how U is defined.
Yeah, that we have to sum over all possible values of V, but yeah. Any other questions? If not, then UMS people will get a short lecture today, and we'll take a short break, and we'll come to convergence theorems for the 690 students.